In this section, we're going to look at applications of Newton's second law to circular motion. Application of Newton's second law to circular motion. Okay. So obviously, circular motion is motion in a circular path. Circular motion. This is motion in a circular path. Okay. So the motion in a circular path. Now, so far we've been using Cartesian coordinate system, this x and y. Okay, but in this case, you see, if you use x and y, and the particle goes along the circular path, both x and y change. Okay, but if you use polar coordinate system, remember polar coordinate system? And a polar coordinate system, points identified by its distance from the center, which we call r, and its angle theta, the angle formed between this line and the positive x-axis, right? In this case, as the particle goes in a circular path, this remains a constant, only this angle that changes. So if you use polar coordinate system, the problem essentially becomes a one-dimensional problem. But if you use Cartesian coordinate system, both x and y will change and becomes a two-dimensional problem. So because of that, it's easier to use polar coordinate system to deal with motion in circular paths. Okay. But before we start, we're going to look at the unit vectors. Okay. We're going to look at the unit vector associated with r and the unit vector associated with theta, just like we did in the case of Cartesian coordinate system. If you remember, the unit vector associated with the x-coordinate was the I unit vector, and the unit vector associated with the y-coordinate was the j unit vector. So we're going to do that for polar coordinate system before we start. So let's look at our unit vector. Obviously, its magnitude is 1, so we just have to define its direction. The direction of this r unit vector is going to be the same as the direction of the change in the position vector while keeping theta constant. So this one has the direction of the change in the position vector while keeping theta constant. That's the definition of our unit vector. Okay, so you see, this is a position vector, right? If you change it while keeping theta constant, this is the only direction it can change. So basically, this unit vector, our unit vector, has the direction of the position vector. But a little bit technical about it. Using this, we can write position vector is its magnitude is r, so you can say r cosine of theta in the I direction plus r sine theta in the j direction. That's what the position vector is. This is x component, this is y component. All right. Now we're saying the r unit vector, we're going to use this notation over here, r unit vector. We're saying its direction is the direction of delta r while keeping theta a constant, and then of course to make it a unit vector, we'll divide it by the magnitude of delta r. Okay, that's the definition of this unit vector according to this definition over here. Okay, so this is r. If you keep theta constant, what do you get? Delta r is only delta r is changing, the theta is not changing. I is a constant vector. You get plus delta r sine theta j. Okay, this is a change in r while keeping theta constant. Only this one changes. Okay, and then the ER unit vector is delta r, that's while theta is a constant, which is this one, divided by the magnitude of delta r, which is this one over here. So the magnitude of this one, you can see very easily, is delta r. Okay, you square this, you take the square root. This will be the magnitude. All right. So we have, this is delta r cosine of theta in the I direction plus delta r sine theta in the j direction divided by the magnitude of the position vector delta r. So if this goes away, we get an expression for ER. So the radial unit vector ER, or the R unit vector, is cosine of theta in the I direction plus the sine of theta in the j direction. All right. So you see that ER is actually parallel to the position vector. Okay. Remember, this is a position vector. Well, let me put this in a box first. So this is a formula for the R unit vector. Okay. Now, you remember the formula for the position vector? This is R cosine of theta in the I direction plus the sine theta in the j direction. Okay, but we just concluded this is ER. Okay, so you've got the position vector R equals the magnitude position vector times ER. In other words, ER is simply the position vector divided by the magnitude of the position vector. Okay, so ER is a unit vector in the direction of position vector. So this implies ER, the radial unit vector, we can call it radial unit vector, or the R unit vector, is a unit vector in the direction of the position vector, position vector. Okay, so let's say you have this position vector over here. This is the direction of the position vector. What we call ER is this vector over here, a unit vector. This is magnitude 1, but in the same direction as the position vector. Okay, so for a particle moving in a circular path, you see, let's say the particle sum over here. This is a position vector, and this is ER, a unit vector in the direction of the position vector. So the direction of the unit vector is radially outward, is in the direction of the position vector. All right. Now, similarly, we're going to look at the theta unit vector. We can also call it a tangential unit vector. Tangential unit vector. Okay. Now, this is also, well, its magnitude is going to be 1. We just have to define its direction. Its direction is the same as the direction of the change in the position vector while keeping R constant. Has the same direction as the direction of the change in the position vector while keeping R constant. Okay, so the direction of this unit vector is the direction of the change in position vector while keeping R constant. So let's see what this means pictorially. Okay, let's say I have a particle moving in this circular path. in the circular path like this. Okay. Okay. We got this position vector over here. Okay. If you change this position vector while keeping R constant, it can only balance circular paths. Okay. So you can only go to this one, which means this change is going to be tangent to the circle. Okay, so the direction of E theta is actually tangent to the circle. If you change this position vector without changing its magnitude, it can only go along the circular path. So this direction is going to be tangent to the circle. Okay, so this tangential unit vector, I'm going to use E theta to represent it, E theta. Okay, according to this definition, E theta would be the change in the position vector while keeping R constant, and then of course dividing by the magnitude of the change. Alright, so what's R? R is R cosine of theta in the I direction plus R sine theta in the J direction. Okay, and dr while keeping R constant is the following. R, the derivative of cosine of theta is negative sine theta in the I direction plus R is a constant, and then R cosine of theta in the J direction, of course, times d theta. This is a change. All right. So now E theta is the dr while keeping R constant divided by the magnitude of dr. Okay, let's do that. Is this divided by the magnitude of this one. All right, so it's going to be this vector negative R sine theta d theta in the I direction plus R cosine of theta d theta in the J direction. And what's the magnitude? You see, when you square this and take square root, sine squared theta plus cosine squared theta is 1. It's simply going to be R d theta. Okay, so I divide this, you get the following for E theta over here. It is negative sine theta in the I direction plus cosine of theta in the J direction. Okay, so this is a formula for E theta. All right. Now, the ER unit vector and the E theta unit vector are perpendicular to each other. Okay, so look over here like this. So you have this circle over here. Okay, so if this is ER in this direction, to the ER, E theta is in this direction. Okay, this is E theta. It's a tangential unit vector. What we're saying is if this is ER, this angle is theta, okay, then E theta is going to be 90 degrees away from that. You add another 90 degrees to this one, this will be E theta. E theta is perpendicular to this unit vector. Okay, so the direction of E theta is tangent to the circular trajectory. Okay, so direction of E theta is tangent to the circle in a counterclockwise direction. In a counterclockwise direction. Okay, so ER is a radial outward unit vector, and E theta is a tangential unit vector in a counterclockwise direction. So if you take off this point over here, this would be ER, this would be E theta. Okay, if we take this point over here, this will be ER, this will be E theta, tangent. If we take this point over here, this will be ER, and this will be E theta, the tangential unit vector. Alright, if we take over here, this is my ER, and this will be theta tangential vector and so on. So ER and E theta are perpendicular to each other. Okay, so we have the following formula for E theta. E theta is negative sine theta in the I direction plus cosine of theta in the J direction, and it is tangent to the circular trajectory. Now we're going to look at the motion variables in polar coordinates. We're going to look at motion variables in polar coordinates. We've been doing this in Cartesian coordinates. Now we're going to do this in polar coordinates. Okay, so the first motion variable is position vector, but we have already obtained expression for the position vector in terms of polar unit vectors. Okay, you remember this one? This is a position vector equals r in the direction of ER. Okay, we have already established that. So in polar coordinates, the position vector is simply its magnitude in the direction of ER. Okay, that's what we mean by motion variables in polar coordinates. That means expressing it in terms of polar unit vectors. Okay, so the position vector is simply its magnitude in the direction of ER, because ER is parallel to the position vector. All right, and then next we're going to look at velocity. As you remember, the definition of velocity is the derivative of the position vector with respect to time. Okay, so this would be the derivative of r in the direction of ER. Now remember, we're talking about motion in a circular path, right? So r is a constant in a circular path. So this derivative only involves ER. But ER, you see, the direction of ER changes as you go in the circular path. So this is a function of time. It changes as a function of time. So the velocity is as follows. The velocity is r, the derivative of ER with respect to time. Okay? Now to evaluate this expression, first let's look at dER with respect to theta. Let's obtain this expression. dER with respect to theta. Okay, this is the derivative with respect to theta, is the rate of change with respect to theta, and this was cosine of theta in the I direction plus the sine of theta in the J direction. Right? So when you do the derivative, you get negative sine theta in the I direction plus cosine of theta in the J direction. But remember this is E theta, okay? This is E theta. So we have the following formula. The derivative of ER with respect to theta is simply E theta, alright? Now let's come back to the velocity. I'll put this in a box. The derivative of ER with respect to theta simply equals E theta. So now we have V equals R times the derivative of ER with respect to dt, okay? Now I can multiply this by d theta over d theta, okay, multiplying by 1, and that is R dER by d theta times d theta by dt, alright? We have already concluded this one over here is E theta, okay? So the velocity is R d theta by dt in the direction of E theta. Okay, now let's look at d theta by dt. If you remember, that's angular velocity, but we compress it as follows. If you remember the definition of a radian, angle in radians, the definition of a radian is this arc length divided by the radius. That's the definition of an angle in radians. Okay, so we have the following formula for angle in radians. It is arc length divided by the radius. Okay, so we're looking at d theta by dt. This is d theta by dt would be, remember, as a constant, so it's 1 over r times ds by dt. But what is, this is, s is distance, so the distance with respect to time is simply speed. This one is speed, v. Okay, so d theta by dt is simply speed divided by the radius. Alright, so let's go back to the formula. So we have v equals radius times d theta by dt in the direction of e theta. But this one, d theta by dt, is v over r, right? R. So you've got v over r for this one in the direction of e theta. Okay, so the radius goes away. We get the following formula for the velocity. It's the magnitude of the speed in the direction of e theta. Okay, so this is the expression for the velocity in terms of polar unit vector. Okay, so what this means is, you see, e theta is tangential to the circle, right? If you take this point, this would be v, which is v in the direction of e theta. Okay, so if you take over here, this would be the direction of this velocity. If you take over here, this would be the direction of the velocity, and so on. It's always tangents the circle in the direction of e theta. All right, and if you want to express it in terms of the angle, then of course v equals v, and this is negative sine theta in the I direction plus cosine of theta in the j direction. Okay, so the velocity in polar coordinate is simply the velocity in the direction of e theta, or if we express in terms of theta, this would be the velocity at any point. And remember, the theta is the direction of the position vector. This is theta. Theta is the direction of the position vector, angle made between the position vector and the x-axis. Okay. So next we're going to look at acceleration. So we're going to use A for this one. Okay. Now, acceleration is the derivative of velocity with respect to time. Okay. But we just concluded that the velocity is simply its magnitude in the direction of e theta. Okay. So the acceleration is going to be the derivative with respect to time of v e theta. Okay, so we're going to use chain rule. This becomes dv by dt in the direction of e theta, and then plus v, the derivative of e theta with respect to time. Okay, now before we do this derivative, first let's obtain let me multiply this by d theta over d theta. Okay, so we've got dv by dt in the direction of e theta plus v d theta by dt, and then I will multiply by d theta over d theta. Okay, so that gives me, this is derivative of the magnitude of the velocity with respect to time in the direction of e theta, and then I can write as follows. I can just move this around. The derivative of e theta with respect to d theta, and then d theta with respect to dt. Okay, so let's try to get an expression for this one. Okay, because we can express in terms of theta, so we can do this derivative, right? So e theta, as we showed before, is cosine, e theta is negative sine theta in the I direction plus cosine of theta in the j direction. Okay, So the derivative of this tangential unit vector with respect to angle is the derivative of sine is cosine, so you get negative cosine of theta in the I direction, and the derivative of cosine is negative sine of theta in the j direction. Okay, now let's factor out the negative. We get the following: this is cosine of theta in the I direction plus sine theta in the j direction. Okay, but this one is the radial unit vector ER. Okay, so we have the following relationship. The derivative of the tangential unit vector with respect to theta is simply the negative of the radial unit vector. Maybe write again. dE theta with respect to d theta is the negative of ER. So we get this relationship. Okay, it's simply the negative of ER. So let's come back to the derivative over here. That is acceleration equals dv by dt in the direction of e theta, and then the second term is v, the derivative of e theta with respect to d theta times d theta with respect to time. Okay, now we're going to use this formula over here. You see this? The derivative of tangential unit vector with respect to theta is simply negative ER. So you get the following. The acceleration is equal to dv by dt in the direction of e theta. Now this is going to be negative v er d theta by dt. All right, and data equals arc length divided by the radius, right? So we just have shown already that this equals 1 over r ds by dt. This is the derivative of arc length, so that's v over r. Okay, so let's put over here. So we've got the acceleration equals dv by dt in the direction of e theta, and then minus v in the direction of er, and this one is v over r. Okay, and so we have the following formula. Acceleration equals the derivative of the magnitude of the velocity in the direction of e theta minus, you see, the square of the speed divided by the radius in the direction of er. Okay, so this is the formula for the acceleration for an object going in circular paths in terms of polar coordinates. Okay, maybe I'll put this in front and write again. So the acceleration in the circular path is negative v squared over r in the direction of er plus derivative of the velocity with respect to time in the direction of e theta. Right? Now you see, as you can see, we have two kinds of accelerations. One is in the direction of ER, the direction of negative ER. Okay, if you take this point, this acceleration over here is direction negative ER. So this acceleration is directed towards the center. Remember, ER is radially outward, so the negative ER is radially inward. And this is acceleration due to change of direction. Okay, you see how this term was obtained? It is the derivative you see this term over here is the derivative of e theta, which is basically the derivative of the direction. This has a unit vector. This is a magnitude of 1. All I have is direction. So this is the change due to change in direction of the velocity. You've got speed and direction. This term is acceleration due to change of speed. Well, this term over here is acceleration due to change of direction, because this unit vector, it has magnitude 1, it has only directional properties. So this is acceleration due to change of direction. So this term over here is acceleration due to change of direction, and it's called centripetal acceleration. Okay, so this is the acceleration due to change of direction. So the term negative v squared r er is always directed towards the center. Is always directed towards the center. It is acceleration due to change in direction. It is acceleration due to change of direction of the velocity. Change of direction of the velocity. Okay? Because of that, it's called centripetal or center-seeking acceleration. It is called centripetal, which means center-seeking acceleration. So if you use AC for centripetal acceleration, we can say AC equals negative v squared over r in the direction of ER. So this is center-seeking acceleration. But the second term, you see, we kept the direction constant and we took the derivative of the speed. So this is acceleration due to change of speed, and its direction is tangents the circle. Okay, so this is our AC, but this acceleration is acceleration due to change of speed. You see, you keep the direction of the velocity, which is tangential, but then you pass the derivative of the velocity over here, and that's called tangential acceleration. Okay, this one is called tangential acceleration. So the term, we're going to put this in the circle, the term dv by dt in the direction of e theta is tangent to the circle, okay, and it is acceleration due to change of speed. It is acceleration due to change of speed. Acceleration due to change of speed. And it's called tangential acceleration. It is called tangential acceleration. Tangential acceleration. So if you use AT for tangential acceleration, we can say AT is the derivative of the speed with respect to time in the direction of e theta. So the acceleration has two components, a direction towards the center called centripetal acceleration, and then an acceleration tangent the circle called tangential acceleration. All right. So let's put this together. In polar coordinates, we have the following. In polar coordinates, we have the following. That is for a circular motion, of course. R is a constant for a circular motion. We have the position vector equal to its magnitude in the direction of the radial unit vector. The velocity equals its magnitude in the direction of e theta, and the acceleration has a radial component v square r in the direction of er, and then a tangential component dv by dt in the direction of e theta. Okay, so these are the polar expressions for the motion variables for a circular motion. Okay. Now let's look at examples. Example. Let's say a particle is moving in a circular path of radius maybe 2 meters, let's say with a uniform speed. Okay. The question is, at point P, express its position vector, velocity vector, and acceleration vectors in polar and Cartesian unit vectors. Okay, so let's identify point P. So let's say this is our circle. Our circle is traveling in this circular path, and its radius is 2 meters. So let's say this part, by the time the particle is over here, this is position vector, right? It's over here. Okay, it's point P. So we're talking about point P. Okay. So the position vector in polar coordinates, the position vector is r in the direction of ER, right? That's it. And r is 2, the radius. R equals 2. So the position vector in polar coordinates is 2 in the direction of ER. Okay, 2 meters in the direction of ER. How about in Cartesian coordinates? In Cartesian, that's in terms of ij unit vectors, we just replace this by this formula. Let's say it's 53 degrees over here. 53 degrees. So this is in polar. Now let's do Cartesian. So you can say r equals, we're going to replace ER by cosine of theta in the I direction plus sine theta in the j direction. Remember, theta is the direction of position vector, so it's this angle over here, okay? So you've got theta equals 53 degrees. So we can say in Cartesian coordinates it is 2, and then cosine of 53 degrees in the I direction plus sine 53 degrees in the j direction. Okay, so the position vector in Cartesian coordinates is 2, cosine of 53 is 0.6 in the I direction, sine of 53 is 0.8 in the j direction. Okay, so in Cartesian coordinates it is 1.2 in the I direction plus 1.6 in the j direction. Okay, this will be the position vector in Cartesian coordinates, and this is the position vector in polar coordinates. So this is for the position vector. Next, let's look at the velocity. Did I specify the speed over here? The uniform speed, let's say, of maybe 5 meters per second. Okay, so the speed is 5 meters per second. So we're going to look at the velocity now. So what we have is the speed is 5 meters per second. Okay, so first polar, let's do polar. The formula for polar is V equals V in the direction of E theta. Now remember, E theta is tangent to this one, so that's what we're talking about. This is V. This is V. It is its speed in the direction of E theta, and E theta is tangent to the circular path. Okay? Alright. But we know V is 5, so that's it. In polar coordinates, this equals 5 in the direction of E theta, meters per second. Okay? That is the velocity in polar coordinates. In polar coordinates, expressed in polar coordinates means express it in terms of the polar unit vectors. Okay, now let's do Cartesian. Well, for Cartesian we have the following formula. We can convert this into I and j using this formula. This is negative sine theta in the I direction plus cosine of theta in the j direction. Remember, theta is the direction of the position vector, so theta is 53 degrees. Okay, so the velocity in Cartesian coordinates is 5, and then that's negative sine 53 degrees in the I direction plus cosine of 53 degrees in the j direction. Okay, so we have, this is sine 53 is 0.8, so we got 0.8, that's going to be negative 4 in the I direction, and then cosine 53 is 0.6, so it's going to be 3 plus 3 in the j direction. Okay, that's meters per second. Okay, so this is the velocity in Cartesian coordinates. This is the velocity in polar and the velocity in Cartesian. Now let's do acceleration. Acceleration. First we're going to polar. Well, the formula for polar for acceleration is this one. Negative v squared divided by the radius in the direction of ER plus dv by dt in the direction of E theta. Okay, now it's going with the uniform speed, so the derivative of the velocity is 0. So uniform speed implies the derivative of the speed with respect to time is 0. Okay, so for this motion, the acceleration simply simplifies to negative v squared over r in the direction of ER. Okay, so we know v equals 5, the radius equals 2, so this equals negative 5 squared divided by 2 in the direction of ER, which is 25 divided by 2, negative 12.5 in the direction of ER, meters per second square. Okay, so this is the acceleration in terms of polar unit vectors. Now let's do Cartesian. Cartesian, all we have to do is replace this in terms of ij, and that formula we know is cosine of theta in the I plus sine theta in the j, and we know theta equals 53 degrees for this particular problem. So the acceleration is negative 12.5, and then cosine of 53 degrees in the I direction plus sine 53 degree in the j direction. Okay, so this is cosine 53 is 0.6, so we've got negative 12.5, and this would be 0.6 in the I direction plus 0.8 in the j direction, meters per second. All right, so that will be the acceleration in Cartesian coordinates. Now let's consider a problem with tangential acceleration. Okay, we're going to add tangential acceleration now. Example. Again, let's say we have a particle moving in a circular path, let's say of radius 2 meters. it is moving with a uniform acceleration. That's a constant acceleration with a uniform, I should say tangential acceleration. Tangential acceleration. Let's say its speed increases from, let's say, 5 meters per second to 10 meters per second, let's say in 2.5 seconds. Okay, so A, express its position vector let's say at point P in terms of polar and Cartesian coordinates. So we've already done this. So if you use the same point over here, it's the same problem we did before. So let's say if you use the same angle, it will be the same thing over here. So it will be R in the direction of ER. Okay, this will be ER. So that is 2 in the direction of ER. And then for Cartesian, it will be 2 cosine of phi3 in the I plus the sine of phi3 in the J. Okay. Now B, express its final velocity. That's when its speed is 10 meters per second. Its final velocity in terms of polar and Cartesian unit vectors. Okay, so the final velocity is 10 meters per second, or it's going from 5 to 10, so the final is 10 meters per second. So in polar, it will be V equals 10 in the direction of E theta, okay, which is meters per second, all right? And in Cartesian, it will be 10, and then you've got this is negative sine phi3 in the I plus cosine phi3 in the J. Okay, so that will be, this will be the Cartesian, this will be the polar. Now let's look at the acceleration. Express its acceleration in terms of polar and Cartesian coordinates. Okay, let's start with polar. The formula for polar acceleration is A equals negative v squared let's say at its final point, that is, the speed is 10 meters per second, all right? So we're treating this point like our final point, okay? Point P is the final point over here, okay? It increases from 5 to 10, and then it has this direction as final point when speed is 10 meters per second. Alright, so this is negative v squared over r in the direction of ER plus derivative of speed with respect to time in the direction of E theta. Okay? Alright, now there is tangential acceleration. This acceleration is uniform, so we can say dv by dt equals delta v by delta t because it's a constant, and the velocity increases from 5 to 10. Okay, it's p final minus p initial divided by delta t. Okay, so that is 10 minus 5. That happens in 2.5 seconds, right? So that is 2 meters per second square. So this is dv by dt. The tangential acceleration is 2 meters per second square. So now we know the speed is 10 at the final point. Okay, at the final point v equals 10. So we have a equals negative 10 squared divided by the radius in the direction of ER plus 2 in the direction of E theta. Okay, so that is 100 divided by 2, negative 50 in the direction of ER plus 2 in the direction of E theta. Okay, that is the acceleration in polar coordinates. Now, to change its Cartesian coordinates, all we have to do is replace this in terms of ij. Okay, now we're talking when the object is at point P, the position vector is p3 degrees. Okay, that's our final point where the direction is p3 degrees. So this equals, maybe let me write on this side. So the acceleration in Cartesian coordinates, we're just going to express ER and E theta in terms of I and j. So ER is cosine of phi3 in the I direction plus sine phi3 in the j direction. Okay, this ER. And then we have E theta, which is negative sine of phi3 in the I direction plus cosine of phi3 in the j direction. Okay, so we have this one, cosine phi3 is about 0.6. Okay, so we've got negative 30 in the I, and this is 0.8, so that's negative 40 in the j. Okay, and then we've got plus 2 times sine phi3 is 0.6, so negative 0.6, that's negative 1.2 in the I direction, and cosine of phi3, this is 0.8, so it's going to be 1.6. Cosine phi3 is 0.6, so that's 1.2 in the j direction. Okay, so after that, we just add i's with i's, j's with j's, so you get negative 30, negative 1.6, that's negative 31.6 in the I direction, and this negative 40 plus 1.2, that is 38.8, negative 38.8, negative 38.8 in the j direction. So that will be in Cartesian coordinates.